Welcome to this comprehensive math tutorial. Today, we'll explore three fundamental topics in algebra that are essential for advanced mathematics. We'll cover quadratic functions and their applications, rational functions, and finally, polynomial and rational inequalities. Let's begin with quadratic functions. A quadratic function is given by the standard form f of x equals ax squared plus bx plus c, where is not equal to 0. The graph of a quadratic function is always a parabola. Quadratic functions have several key features. The vertex is the highest or lowest point on the parabola located at the point h, k, where h equals negative b over 2a and k equals f of h. The axis of symmetry is a vertical line passing through the vertex with equation x equals h. The y-intercept is at the point 0, c, and the x-intercepts, also called roots, are found by solving the equation ax squared plus bx plus c equals 0. Let's work through an example. Find the vertex and x-intercepts of the function f of x equals 2x squared minus 8x plus 3. First, we calculate h, which is negative b over 2a. That's negative of negative 8 over 2 times 2. This simplifies to 8 over 4, which equals 2. Next, we calculate k by evaluating f of 2. That's 2 times 2 squared, minus 8 times 2 plus 3. This gives us 8 minus 16 plus 3, which equals negative 5. So the vertex is at the point 2 minus 5. Now, let's find the x-intercepts by solving the equation 2x squared minus 8x plus 3 equals 0. We'll use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Substituting our values, we get x equals 8 plus or minus the square root of negative 8 squared minus 4 times 2 times 3, all divided by 2 times 2. Simplifying, this becomes x equals 8 plus or minus the square root of 64 minus 24, all over 4. That's 8 plus or minus the square root of 40, all over 4. The square root of 40 equals 2 times the square root of 10. So, x equals 8 plus or minus 2 times square root of 10, all over 4, which simplifies to 2 plus or minus the square root of 10 over 2. These are our x-intercepts. Quadratic functions have many real-world applications. They can be used to model projectile motion, optimize area or revenue, and describe many physical phenomena. For example, the height of a projectile can be modeled by the function h of t equals negative 16t squared plus v naught t plus h naught, where v naught is the initial velocity and h naught is the initial height. In economics, revenue functions often have a quadratic form, where we want to find the price that maximizes revenue. Now, let's move on to our second topic, rational functions. A rational function is defined as r of x equals p of x divided by q of x, where p and q are polynomials, and q of x is not equal to 0. Rational functions have several key features. The domain excludes zeros of the denominator. Vertical asymptotes occur at zeros of the denominator, unless cancelled by factors in the numerator, and horizontal or slant asymptotes depend on the degrees of the numerator and denominator polynomials. The behavior of the horizontal asymptote depends on the relationship between the degrees of p and q. If the degree of p is less than the degree of q, the horizontal asymptote is at y equals 0. If the degree of p equals the degree of q, the horizontal asymptote is at y equals the ratio of the leading coefficients. If the degree of p is 1 more than the degree of q, there's a slant asymptote found by polynomial long division. Let's analyze an example. R of x equals x squared minus 1 divided by x squared minus 4. First, we factor the numerator and denominator. The numerator becomes x minus 1, x plus 1, and the denominator becomes x minus 2, x plus 2. The domain excludes x equals 2 and x equals negative 2, which are the zeros of the denominator. There are vertical asymptotes at x equals 2 and x equals negative 2. Since the degrees of the numerator and denominator are both 2, the horizontal asymptote is at y equals the ratio of the leading coefficients, which is 1. No factors cancel out, so there are no holes in the graph. Finally, let's discuss polynomial and rational inequalities. These are expressions where we need to find all values of x that make the inequality true. The key to solving these inequalities is to find the critical points where the expression equals 0 or is undefined, create a sign chart, and test intervals. Let's solve a polynomial inequality x cubed minus 4x squared plus x plus 6 is greater than 0. First, we factor the expression as x minus 2 times x minus 3 times x plus 1. The critical points are x equals -1, x equals 2, and x equals 3. These points divide the number line into 4 intervals: less than -1 between -1 and 2, between 2 and 3, and greater than 3. Now, we create a sign chart to determine the sign of the expression in each interval. To determine the sign in each interval, we test a point in each interval. For x less than -1, the signs are negative, 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 giving a negative product. For x between -1 and 2, the signs are negative, negative, positive, giving a positive product. For x between 2 and 3, the signs are positive, negative, positive, giving a negative product. For x greater than 3, all factors are positive, giving a positive product. Therefore, the solution to our inequality is -1 is less than x is less than 2, or x is greater than 3. We can visualize this on the graph of the polynomial. Now, let's solve a rational inequality. X plus 3 divided by x minus 1 is greater than or equal to 0. First, we identify the critical points x equals -3, where the numerator is 0, and x equals 1, where the denominator is 0. These points divide the number line into 3 intervals: less than -3, between -3 and 1, and greater than 1. Testing a point in each interval. For x less than -3, both the numerator and denominator are negative, giving a positive result. For x between -3 and 1, the numerator is positive, but the denominator is negative, giving a negative result. For x greater than 1, both are positive, giving a positive result. Therefore, the solution is x is less than or equal to -3, or x is greater than 1. Note that x equals 1 is excluded from the domain. In conclusion, we've covered 3 essential mathematical topics: quadratic functions, which form parabolas and have applications in optimization and physics; rational functions, which involve fractions of polynomials and feature vertical and horizontal asymptotes; and polynomial and rational inequalities, which we solve by identifying critical points and analyzing the sign changes. These concepts form the foundation for many advanced topics in calculus and higher mathematics. Remember to practice these methods with various examples to gain confidence in applying them.